Alright, let's go. Number 10, the holographic boundary. In 1972, Jacob Bekenstein was a graduate student at Princeton trying to solve a mundane thermodynamics problem. Could you violate the second law by dropping a hot cup of tea into a black hole? The entropy would seem to vanish into the horizon. His advisor John Wheeler thought it was a nice question. Bekenstein went looking for a boring answer. Standard physics says entropy is a property of volume. A three-dimensional object stores information in 3 dimensions. Double the size, you get 8 times the information. That is how every object we have ever measured behaves: a gas cloud, a hard drive, a human body. Black holes don't do this. Bekenstein found their entropy scales with surface area, not volume. Double the radius, you get 4 times the information, not 8. In his 1973 paper in Physical Review D, Bekenstein proposed that a black hole's entropy equals 1/4 of its event horizon area, measured in Planck units. Stephen Hawking confirmed the formula 2 years later in Communications and Mathematical Physics, deriving it from quantum field theory in curved spacetime. Every physicist who tried to break it failed. Physicists tried to reduce this to a curiosity. It wasn't. They tried to say it only applied to black holes. Gerard 't Hooft showed in 1993 it applied everywhere. They tried to interpret the surface encoding as a coordinate trick. Juan Maldesena's 1997 adds CFT paper in Advances in Theoretical and Mathematical Physics proved the encoding was real. A lower dimensional theory on the boundary was mathematically equivalent to the higher dimensional theory inside. Every test since has held. If the principle applies to our universe, the 3 dimensions you appear to move through are a projection. The real information, every thought, every memory, every heartbeat happening inside you right now is encoded on a 2-dimensional surface at the edge of the observable universe. You have never seen that surface. You never will. But it may be where you actually are. A black hole's edge is one boundary. Its center is a different problem. Number 9, the Quark-Gluon plasma at singularity conditions. In the 1970s, particle physicists working on quantum chromodynamics, the theory of the strong force, were trying to explain why quarks never appeared alone. Every experiment showed them locked inside protons and neutrons. David Gross, Frank Wilczek, and David Politzer wanted a clean mathematical answer to a laboratory puzzle. The standard model predicts quarks are permanently confined at normal energies. Try to pull one out of a proton, and the energy required creates a new quark-antiquark pair before you succeed. Confinement is not a suggestion. It is a hard boundary of matter as we know it. At sufficient temperature and density, confinement fails. Quarks and gluons flow freely as a plasma. The state has been confirmed at temperatures around 4 trillion Kelvin. In 2010, the STAR and Phoenix collaborations at Brookhaven's Relativistic Heavy Ion Collider published results in Physical Review letters confirming quark-gluon plasma behaves as a nearly perfect fluid, with viscosity approaching the theoretical minimum set by Pavel Kovtun, Dom Sun, and Andrei Starinets at UC Santa Barbara in 2005. They're bound. IRs Mars RSP. Nature obeys it exactly. Physicists assumed the QCD phase diagram at higher densities would follow the same pattern. It doesn't. Lattice QCD calculations break down at high chemical potential due to the sign problem, a mathematical obstruction identified by Philippe de Fourcron at ETH Zurich, unresolved for 4 decades. Every attempt at analytic continuation has failed. Every proposed effective theory disagrees with the next. At densities approaching a black hole's core, no framework works at all. The matter that once formed your body's atoms, hydrogen forged in the first minutes after the Big Bang, carbon in an ancient star, would not be matter inside a black hole. It would be something with no name, no equation, no experimental analog. Whatever your atoms become down there, we do not know how to describe it. Below the plasma is a place the mathematics says exists somewhere else entirely. Number 8, the white hole interior. In 1960, Martin Kruskal at Princeton and George Seekers in Australia were working independently on a boring cartography problem. Einstein's Schwarzschild solution had a coordinate singularity at the event horizon that made calculations messy. They wanted cleaner coordinates. Nothing more. The Schwarzschild solution describes a black hole formed by collapse. A star's mass compresses, an event horizon forms. Matter falls in and never comes out. This is the picture every textbook uses. It is also incomplete. When Kruskal and Seekers extended the coordinates to cover the full mathematical solution, they found 2 extra regions no one expected. One was a white hole, a time-reverse black hole that only expels matter. The other was a second exterior universe. Kruskal's paper appeared in Physical Review in 1960. Shaker is published in Publicaciones Mathematicae de Bresson the same year. The maximally extended Schwarzschild geometry has 4 regions. Our exterior, the black hole interior, a white hole, and a parallel exterior connected by an Einstein-Rosen bridge, a wormhole. The mathematics does not treat any of the 4 as more real than the others. Physicists tried to dismiss the extra regions as mathematical fiction. John Wheeler and Robert Fuller showed in 1962 in Physical Review that the wormhole exists but pinches off faster than light before anything can cross it. Others argued the white hole region only appears in eternal black holes, not ones formed by collapse. But eternal black holes are the exact solutions. The collapse case is the approximation. Which one is the real universe answering? If a white hole region exists and is causally disconnected from ours, everything that has ever fallen into a black hole may be emerging somewhere we cannot see, into a universe we cannot reach, in a time we do not share. The mathematics does not tell us whether that place is real. It only tells us the equations do not forbid it. The next region the equations do not forbid is stranger. It has less than nothing. Number 7, negative mass regions. In 1963, New Zealand mathematician Roy Kerr was trying to solve a technical problem. Einstein's field equations for a non-rotating black hole had been solved by Carl Schwarzschild in 1916. Every star rotates. Kerr wanted the rotating solution. He spent 6 months on it in Austin, Texas. A rotating black hole should have a similar structure to a static one, an event horizon, a singularity at the center, everything ordered by mass and spin. The mathematics should produce a slight distortion of the Schwarzschild solution. Nothing exotic. Kerr's solution had 2 horizons instead of 1. Between them lay a ring-shaped singularity, not a point. And inside the inner horizon, the Penrose diagram showed a region where the effective gravitational mass turned negative. Kerr published in Physical Review Letters in 1963. Roger Penrose extended the geometry in the Revista del Nuovo Cimento in 1969. Brandon Carter's 1968 paper in Physical Review mapped the causal structure completely. Inside the inner Cauchy horizon, closed time-like curves become possible and gravitational effects reverse sign. Objects near the ring experience repulsion from mass, not attraction. Physicists proposed the inner horizon was unstable. Small perturbations would collapse it before anything reached the negative mass region. Werner Israel and Eric Poisson developed the mass inflation instability in Physical Review D in 1990, but numerical simulations by Amos Ori at the Technion in 1991 showed the inner horizon might survive as a weak null singularity. Objects could still cross. The negative mass region is still there in every valid Kerr solution the mathematics permits. If you fell into a rotating black hole and somehow survived the inner horizon, you would find yourself repelled from the very mass that pulled you in. The direction of gravity would invert around your body. Whether anything can survive that crossing is a question no experiment can ever answer. Some theorists believe there is no interior to cross at all. Number 6, the Fuzzball Hypothesis. In the late 1990s, Samir Mather at Ohio State University was working on a bookkeeping problem in string theory. Every consistent string theory needed to reproduce the Bekenstein-Hawking entropy of a black hole by counting its internal quantum states. Andrew Strominger and Kumran Vafa at Harvard had done it in 1996 for special extremal cases. Mather wanted to know where those states actually lived. In general relativity, a black hole is empty space, with a singularity at its center and an event horizon marking the boundary. The interior is smooth. The singularity is a mathematical point. Nothing exists between. Mather found the interior is not empty. The microstates counted by string theory occupy the entire volume. There is no singularity. There is no smooth interior. The event horizon is not a surface. It is the outer edge of the object itself. Mather's foundational review paper appeared in Fortschritte der Physik in 2005. Follow-up work with Oleg Lunin at Ohio State, published in Nuclear Physics B, showed that individual microstates have no horizon at all. They are fuzzballs of tangled strings and brains at Planck density. Critics argued the fuzzball construction only worked for special extremal black holes, not realistic astrophysical ones. Mathur and Yosef Bena at the Institut de Physique Théorique in Saclay extended it to near extremal cases in papers through 2015. Others argued no external observer would ever detect the difference from a classical black hole. Recent work suggests they would. The reflection of infalling matter would produce gravitational wave echoes. Every clean escape from the picture has closed off. If the fuzzball picture is correct, nothing that has ever fallen into a black hole reached any interior. The matter simply became part of the surface, smeared into a tangled structure at the boundary you can never cross. Where do you go if there is no inside to fall into? The question of where you go leads to a stranger question about when. Number 5. Closed time-like curves. In 1949, Kurt Gödel was preparing an essay for a volume celebrating Einstein's 70th birthday. The two were close friends at the Institute for Advanced Study in Princeton. Gödel wanted to give Einstein something interesting, a new solution to the field equations. He chose a rotating universe. General relativity permits many solutions. Most describe universes that behave sensibly. Matter attracts, time moves forward, causes precede effects. The field equations do not enforce these behaviors. They only require internal consistency. Gödel's rotating universe permits closed time-like curves. Following certain paths through spacetime, a traveler returns to their own past. Not metaphorically. The mathematics produces literal time loops. Gödel published in Reviews of Modern Physics in 1949. Frank Tipler at Tulane extended the result in Physical Review D in 1974, showing that any sufficiently long rotating cylinder produces closed time-like curves, and that the interior of a curved black hole contains them naturally. Stephen Hawking spent the last 3 decades of his career attempting to rule them out. He proposed the chronology protection conjecture in Physical Review D in 1992. He could not prove it. Physicists proposed that quantum effects would destroy any closed time-like curve before a traveler could use it. Kip Thorne at Caltech modeled the effect through the 1990s. In some cases, the curves collapse. In others, they don't. Others argued the required energy conditions violate quantum field theory. Larry Ford and Thomas Roman found that quantum fields themselves violate those energy conditions locally. Every proposed prohibition has exceptions. Inside a rotating black hole, and every real black hole rotates, paths exist that loop your future back into your past. Your memory of what happens there would be a memory of something you would then be forced to cause. What does it mean to remember an event you have not yet created? If we cannot rule out time loops, we may not be able to rule out echoes either. Number 4, the echo signals. In September 2015, the LIGO detectors in Louisiana and Washington recorded the first direct detection of gravitational waves, 2 black holes merging 1.3 billion light-years away. The team spent 5 months verifying the signal. Nyayesh Afshorty's group at the Perimeter Institute was doing something quieter. They were looking for what came after. General relativity predicts a clean signal, inspiral, merger, ring down. The ring down is a series of damped oscillations as the newly formed black hole settles. It should fade smoothly into detector noise. There should be nothing after. There was something after. Faint pulses appeared roughly 0.1 seconds behind the main signal, echoes at frequencies predicted years earlier by Ahmed Farag Ali and collaborators if Planck Stars or fuzzballs replaced the classical event horizon. Jahed Abedi, Hannah Dakar, and Nyayesh Afshorty published the first echo detection in Physical Review D in 2017, claiming a 2.9 sigma signal, statistically suggestive but not conclusive. Julian Westerweck's team at the Max Planck Institute reanalyzed the data in 2018 and reported the significance was lower. Randy Conklin, Bob Holdham, and Jing Ren at the University of Toronto found the signal again in 2018 at higher confidence. 3 independent teams. 2 confirmed, 1 retracted. Critics argued the echoes were artifacts of the LIGO noise model. New noise models were built. The signal persisted at some frequencies and vanished at others. Others argued the templates used to search were too flexible. You can find any signal if your template allows it. Restricted templates found weaker signals. Broader templates found stronger ones. The signal has not been ruled out. It has not been confirmed. Nearly a decade on, the disagreement is exactly where it was. If the echoes are real, every black hole detection since has been carrying a signature that the classical picture forbids. The event horizon may not be a horizon at all. You would be listening to something bouncing off a wall we said did not exist. The data has not changed, only the theorists have. The theorists disagree about what happens inside. They disagree about what direction inside even is. Number 3. Time inversion zones. In 1916, Karl Schwarzschild was serving on the Russian front in the German army. He calculated the first exact solution to Einstein's field equations in his spare time between artillery calculations and mailed it to Einstein from the trenches. He died a few months later of an autoimmune disease contracted in combat. He never saw what his solution implied about the region inside the horizon. In normal space, you can move freely through 3 spatial dimensions. Time moves forward whether you like it or not. Space is optional. Time is mandatory. This asymmetry is the deepest feature of the universe you inhabit. Inside a Schwarzschild black hole's event horizon, the radial coordinate distance from the center behaves mathematically like time. The time coordinate behaves like space. Falling toward the singularity becomes as unavoidable as aging. The behavior was first analyzed rigorously by David Finkelstein at the Stevens Institute of Technology in 1958, published in Physical Review. He showed that inside the event horizon, the roles of the r and t coordinates swap in every physically valid coordinate chart. Every time-like world line inside must terminate at r charge 0. The singularity is not a place at the center. It is a moment in the future. Physicists tried to interpret this as a coordinate artifact. Roger Penrose's causal diagrams in 1965 showed it wasn't. Some argued rotating black holes avoided the effect. Brandon Carter's analysis of the Kerr metric confirmed a similar structure between the outer and inner horizons. Others suggested quantum effects near the horizon would dissolve the classical geometry before the swap occurred. No proposal has demonstrated this at horizon crossing. The swap is written into the equations that agree with every test we have ever performed. If you crossed the event horizon of a Schwarzschild black hole, you would not fall toward the center. The center would move towards you the way tomorrow moves toward you now. You cannot avoid tomorrow. You cannot avoid the singularity. What is a self when the direction of your body's future is a place? If the future is a place, some equations say it might not have to be reached. Number 2. Planck Stars. In 2014, Carlo Rovelli at Aix-Marseille University and Francesca Vidotto at Radboud University were working on loop quantum gravity, an alternative to string theory that tries to quantize space itself. They wanted a testable prediction. Something concrete that classical general relativity forbids. General relativity says collapse continues to a singularity, infinite density, infinite curvature, the end of predictability. Every calculation, every simulation, every extension of Einstein's equations converges on the same conclusion. The center of a black hole is a mathematical point where physics stops. In loop quantum gravity, space cannot be compressed below a minimum area, roughly 10 to the power of minus 66 square centimeters, set by the Planck length. Collapse cannot reach a singularity. It bounces. Rovelli and Vidotto published Planck Stars in the International Journal of Modern Physics D in 2014. The predicted bounce compresses matter to Planck density, around 10 to the power of 93 grams per cubic centimeter, before reversing. The full bounce takes a time proportional to the black hole's mass squared. For a stellar black hole, that is roughly 10 to the power of 71 years. For primordial black holes formed shortly after the Big Bang, it could be happening right now. Critics argued the bounce would violate the second law of thermodynamics. Entropy would decrease when the black hole released its contents. Aurélien Barraud at Grenoble showed in a 2016 paper in Physics Letters B that the outgoing radiation preserves entropy through quantum correlations. Others argued the collapse timescale inside would prevent any observable signature. Hal Haggard and Rovelli calculated the observable delay in Physical Review D in 2015 and found it detectable. Others insisted no primordial black holes existed in the right mass range. The 20-20 microlensing surveys have not ruled them out. Every atom that has ever fallen into a black hole may still exist. Compressed, waiting in a state that will one day be returned to the universe long after every civilization you know is gone. What comes back out, when it comes, will not be what went in. What went in and what comes out may not even agree they are in the same universe. Number 1, the Firewall Paradox. In 2012, Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully at UC Santa Barbara were working on a problem Stephen Hawking had raised nearly 40 years earlier. Hawking radiation slowly evaporates black holes, but the radiation appears thermal, random. If it is random, information falling in is destroyed. If information is destroyed, quantum mechanics is violated. The team wanted a clean resolution to a very old debate. Quantum mechanics requires information to be preserved. General relativity requires the event horizon to be an unremarkable region of spacetime. A freely falling observer should notice nothing crossing it. Both principles have been confirmed thousands of times in independent experiments over a century. Almhary and colleagues proved the two principles are mutually incompatible. If information is preserved, the event horizon cannot be smooth. There must be something waiting there, a wall of high-energy quanta that incinerates anything crossing it. A firewall. The AMPS paper, named for the four authors, appeared in the Journal of High Energy Physics in 2013. It formalized a paradox first hinted at by Samir Mathur in a 2009 paper. The effective temperature of the firewall would be near the Planck scale, around 10 to the power of 32 Kelvin. Anything falling in would be vaporized at the horizon, contradicting a century of confirmed general relativity. Juan Maldacena and Leonard Susskind proposed Schacter's EPR in 2013 in Fortschritte der Physik that entangled particles are connected by microscopic wormholes, dissolving the paradox. It works in some limits and fails in others. Daniel Harlow and Patrick Hayden proposed the computational complexity resolution. The firewall exists, but no observer could ever verify it before falling in. This survives, but only by making the answer permanently untestable. Every clean resolution has failed. Every physicist who reads the AMPS argument agrees the conclusion follows from the premises. No one has removed a premise. Either quantum mechanics is wrong, or general relativity is wrong, or your intuition that falling in is something that happens smoothly is wrong. One of the three pillars of modern physics is not what it seems. You are held together by both theories at once. If they cannot both be right at a black hole's edge, they cannot both be exactly right anywhere. Every entry on this list sits not at the edge of physics, but at its center. The Schwarzschild solution is a century old. Quantum mechanics is older. Baconstein's formula, Kerr's rotation, Gödel's loops, these are not fringe ideas at the margins of the field. They are what our most tested theories say happens when we follow them past the point we can see. The universe is not confused about any of this. We are. And the confusion is written into the equations we use to describe the ground you are standing on right now. If you want to see more videos like this, click the video on screen now.